I've disappeared from YouTube for about a month, and there's been a lot of speculation as to where I've been. The truth is, I've actually been putting all my effort into engineering one project. You may remember, last year I built a hand cycle and rode it across Switzerland. And on that trip I had a lot of problems, most notably being having a way to charge it and having a way to keep all my camera gear charged. Well, not anymore. In this video, we're going to be creating a power station, but not like the one I built a couple of months ago. No, this is going to be the ultimate camping power station. Since my last power station, a lot has changed, both with me and with what's available on the market. But the most notable thing is, last time I didn't have this video's sponsor, PCBWay. PCBWay aims to simplify the process of taking your product from design to prototype. Ordering through PCBWay is simple. Upload your file, select the options you want from their vast number of manufacturing services, and allow their instant quote feature to give you real-time feedback on how your different choices change the final price. If you're interested in designing a product or following along with this video, be sure to check out PCBWay in the link in the video description. When tackling big projects, it's sometimes difficult to know where to start. But with something like a power station, it's a lot easier because most of the components revolve around the size and style of battery I'm using. So that seems like the obvious place to start. But the question is, what batteries are we going to be using? There's a vast number of different battery options out there on the market, from lithium-ion batteries all the way to lead-acid batteries. Of the many different types of batteries on the market, for this project I decided I was going to use lithium iron phosphate batteries, or LiFePO batteries. And this is because they have a significantly higher cycle count than other types of batteries. Whereas lithium batteries typically die around 2000 cycles, LiFePO batteries can go much longer than that, up to some reaching nearly 10,000 cycles. For this project, I'm going to be using 3.2 volt 35 amp hour cells from a company called Eve. Side note, if you are following along at home, Eve make a form of these batteries with screw terminal connections instead of the flat plates, and I would recommend using them. So I'm going to link them in the description instead of these batteries. You will have to slightly alter the connection plates, but I'll put the two different models and all the 3D files in the In order to hold all these cells together into one battery, I'm going to 3D print an enclosure using my Creality K1 Max. I'm going to 3D print it at 100% infill out of PETG plastic. To make my life easier, I decided that I would just make the batteries slot into this base plate and have all the conductors in a top plate. For the top part of this, I'm going to first 3D print a top plate out of TPU. I'm then going to use our sponsor PCBWay to manufacture some contact plates which I can fit into that TPU plate. With the plate printed, we just have to wait for the parts from PCBWay. Luckily for us, a package from PCBWay has arrived. Let's crack this open. As you can see, we've received high quality parts with good finishing, and of course everything is within tolerance. Let's get on to building the battery now. According to my design, these pieces should fit nicely into these slots, and for me they do. So let's secure it in place. The reason I use TPU for this is that I'm planning to cause a lot of internal stress to make sure that there's good connections. And in order to do that, I'm going to tighten the bolts on the edge down a lot to cause the TPU to flex. It was important that I printed it at 100% infill, otherwise I could end up with the TPU kinking. In order to complete the circuit, I'm going to be using grub screws to connect to the batteries. Now, it's important here that you use aluminium or brass grub screws as opposed to steel grub screws. And the reason for that is steel has significantly lower conductivity than brass or aluminium. Considering the price of aluminium though, I decided to go with some brass ones I had lying around. These grub screws wouldn't work, however, for the positive and negative terminals. So for them, I used some 6061 threaded bar. The final thing we need to do is build a battery management system. Even though LiFePO batteries are significantly less volatile than other types of lithium-ion batteries, overcharging and over-discharging them can cause significant damage to them and decrease the lifespan of the batteries. So how does one go about designing a BMS? Well, before we can start designing, we have to know exactly what we're trying to do. And it's basically just a series of checks. Check that the temperature is within range, check that the voltage of each cell is within range, and check that the current is within range. That's it. If any of them go out of range, we have to turn off the battery, which can be done quite easily using MOSFETs. So let's give this a go. For the brains of this, I'm going to use an Arduino Nano and connect each cell to an analog pin through a potential divider. By selecting the correct resistors, I can keep the cell voltages right in the middle of the Arduino's ADC range. And by using such high resistor values, even if something does happen and higher voltage gets put through them, it won't damage the Arduino because there simply won't be enough current to do any significant damage. In order to measure the current, I'm going to be using something called a current shunt. And what this is where you take a known resistor and measure the voltage drop over it. Using Ohm's law, you can then calculate the current. In my case, I'm going to actually be using the drain source resistance of the MOSFETs because I know that in the on state, the drain source resistance of these particular MOSFETs is 17 milliohms. And to get 5-volt power to the Arduino, I'm going to use a DC to DC converter. I quickly whipped up a schematic in KiCad before moving on to building this on a perf board. The final thing to do was write some code and upload it to the Arduino. Now that the battery's complete, I think the next logical step is to build a charger. And you might be thinking, why don't I just buy one and plop it in? Well, the answer is I basically don't have the features I want on commercially available chargers. I want to be able to charge my battery off mains electricity, but I also want to be able to charge my battery off solar power. So that means we're going to have to build our own. And in order to do that, we need to much better understand how charging of LiFePO batteries works. Stage 1. Let's start with stage 1. Stage 1 is constant current charging. And this is where the charger delivers a constant current to the battery. It does this by varying the voltage, specifically increasing the voltage to increase the current and decreasing the voltage to decrease the current. As the battery gets more charged, more voltage is required to maintain that same current. And when it's at about 75 to 80%, that voltage required would exceed the maximum voltage of the battery, which is when we switch to stage 2. Stage 2 is constant voltage charging. And in this charging, we hold it at the maximum voltage of the battery. And the battery starts to absorb energy. This takes it from 80 to 100%. This is more degrading on the battery and is why it's often better to only charge your phone or other lithium battery to 80% so that you can maintain a higher charge cycle life. So let's build a charger. So how do we build a charger like this? Well, that depends on who you ask. There are a lot of different ways to do it. Cheaper battery chargers like this one will step your input voltage down to the maximum voltage of your battery and then use a resistive constant current driver to limit the current. When that's wide open, the voltage can't go above the input voltage. That is junk for a number of reasons, but it loses a lot of energy because basically it dumps all the extra energy as heat. So what I'm going to use instead is a switch mode power charger. In order to build this charger, I'm going to be using something called a buck converter, which is a form of DC to DC switch mode power supply. The way it works is quite simple. In principle, there are four components: an inductor, a capacitor, a diode, and a switch. When the switch is closed, current will flow from the voltage source through the inductor and out to the output. However, when we open the switch, the inductor will try and maintain that current. And in order to do that, it will pull voltage through the diode. And if we replace that switch with a high-frequency signal, the output voltage is directly proportional to the input voltage times the duty cycle. There are many integrated circuits on the market for controlling switch mode power supplies, and by selecting the correct one, I can have a constant current, constant voltage power supply using a current shunt, much like we did with the BMS. Only this time the resistance is going to be a little bit higher, around 3 ohms, which will generate some loss, but it shouldn't be too significant. We can now charge this with a range of DC voltages, anything from about 15 volts upwards, which is great because it means we can charge it off solar. The problem comes when we have to charge it off 240 volt mains electricity. But that's an easy solution. I'll simply use a flyback converter to take our mains electricity and step that down to around 20 volts DC. I can then feed that into our buck converter and charge the battery that way. The final circuit looks pretty much like this. We have the AC input going through the flyback converter and then into the buck converter. We also just have the DC input going straight into the buck converter. Now that we have a battery that charges, it's time to start looking at outputs. I have two different outputs I want to use, an AC output and a USB output. For the AC output, I'm going to be using this true sine wave inverter I purchased online. I was going to build my own, but this video is already very long and I didn't want to make it any longer. As for the DC output, this is where it becomes clear why I used such a chonktastic 12 to 5 volt converter. Because the DC USB output is actually a PD board which runs off 5 volts. The system here is pretty simple. The power from the inverter is just the output from the BMS, and the power for the USB board comes directly from that 5 volt regulator. We now pretty much have a functional power station. We have charging, we have power output, and we have USB output. But I don't really like the fact that everything's always on. Not only is it inefficient, drawing around 1 amp at idle, it's also horrendously dangerous. Imagine if we got water in the plug and couldn't turn it off. Luckily, there's a simple solution to this. Remember when I used an Arduino earlier, and it was incredibly overkill for the BMS? Well, there was a reason behind that. And that is because I can use the other pins on the Arduino to control different aspects. So I've connected up each Arduino pin through some circuitry to a relay. And now we have an Arduino pin controlling the on-off of the inverter and on-off of the power supply for the USB. That wasn't a great explanation, but basically relays require more power than an Arduino can supply. So we need something called a relay gate driver. This basically just boosts the signal and creates a high enough level of signal for the relay to flip. After looking online, it turns out you can get specifically designed relay gate drivers for Arduino, so I'll put a link to some of them in the video description. I think I'm going to call it there for this video. I'll 3D print a case and then we can test it out in a sec. But I wanted to add some more functionality like a screen, some better buttons, Bluetooth functionality, and an estimate of how much time it had left. Unfortunately, all of these things I wanted to add were in one shipment. and the delivery driver left that outside. It got rained on, and of course all the electronics inside it were dead on arrival. I'm definitely going to be making a part 2 where I finish this project, but unfortunately with that delay, I'm not going to be able to finish it for quite a while because some of those parts are out of stock and I'll have to redesign the internals for it.
This box isn't going to be final, but it's just so we can test it out. I know at this point a lot of you are thinking, blimey, that really didn't explain how to build a power station. Well, that's because we need a lot more time to do that. And in order to do that, we're going to make a series of videos over the next couple of weeks explaining each part in more detail. Anyway, for now, let's test it. Man, this box is really crap. Let's give it a test. Starting off easy, a 60-watt video light. This should have no problem at all. Hold on. Here we go. And, well, not a huge shocker there. The 60-watt video light didn't break the 600-watt power station. Let's step up the game. Okay, now we actually are stepping up the game. This is my All Powers R600. It's quite heavy. Now we really are stepping up the game. All Powers R600. This charges at 300 watts. Let's stick that in somewhere. We need some more power. Let's plug in my laptop, which charges at 150 watts. Well, there we go. Right, well there we go. We've got 60 watts, 150 and 300. Damn! This was a great success. We have 60 watts, 300 watts and 150 watts, so totaling 510 watts. And that's just a little bit over the 500 I designed this for. Tune back in next week and we'll be taking a look into how to charge lithium batteries, specifically these ones. And over the course of the next couple of weeks, we're going to be stripping this down, redesigning it and making it the ultimate power station. Hopefully better than the All Powers one I have. Alright, see you next week.